Swayam Prabha. Digital India. Educated India.
Hello students, welcome to today's lecture. In last few lectures, we have been discussing the hydrogen atom problem and its quantum mechanical solution. We would continue our discussion from where we left, but before that, since we did a lot of derivation, so therefore, it would be helpful if we go through some of the important points that we discussed in our last few classes. If you remember, we discussed the hydrogen atom where one electron is going around the nucleus. So, therefore, we could write the Hamiltonian of the system as two kinetic energy operators, one corresponding to the nucleus, the other one corresponding to the electron, plus the potential energy of interaction between the two. And when we are discussing the potential energy, we expressed this as a Coulomb interaction between the two charged particles, that is the electron and the nucleus. Since we have this two body problem, we changed this two body problem to two effective one body problems, where the first term represents the overall translational motion of the center of mass with a fictitious mass of the nucleus and the mass of electron. The second term that we see relates to the internal degree of freedom or the kinetic energy associated with the internal degree of freedom, that is the distance between the electron and the nucleus. To get this kinetic energy term and the potential energy term together, they constitute the internal Hamiltonian of the system. In other words, we also can express these two terms. The first term, since it involves the mass of nucleus and the mass of electron and the center of mass of the two body system, and since the mass of nucleus for hydrogen atom is at least 3 orders of magnitude greater than the mass of the electron. So, therefore, this center of mass movement is essentially dictated by the movement of the nucleus. So, the first term is the nuclear degree of freedom or the movement of the nucleus. The second term, which contains the reduced mass mu, again for the same reason that the mass of electron is at least 3 orders of magnitude less than the mass of nucleus, the reduced mass will be dominated by the mass of the electron. So, therefore, the second term becomes the kinetic energy associated with the electron, and the third term is our potential energy. So, we started with this Hamiltonian and we said that we can separate this first term with from the second and third term, and we looked at the internal motion of the system. So, we started from this Hamiltonian and we wrote down the Schrodinger equation, where this Laplacian is expressed in terms of spherical coordinate, where r is the radial part and this lambda square, which is the Legendrian function, this depends on theta and phi, the two angular coordinates of our system. This is our Hamiltonian for the kinetic energy part of the Hamiltonian, this is the potential energy, and we wrote down the Schrodinger equation. When you look at the Schrodinger equation, we say that this wave function that we still do not know what it is should depend on r, theta and phi variables, because we see our operator having dependence on r, theta and phi. Then other thing that we saw is that when I look carefully at this operator, I see there is only one term, the Legendrian term, which has theta and phi dependence. The rest of the terms have r dependence. So, therefore, I said that let us express this total wave function as product of two functions, one is radial, another is angular. So, essentially we did a variable separation technique. So, we expressed our total wave function as product of two functions, one is the radial function, another is angular function. When we what angular function could we take? We see that this is lambda square operator, which is closely related to L square, the orbital angular momentum operator. So, therefore, the angular functions that we should take can be the spherical harmonics. They are simply they are the eigenfunctions of L square operator. Once we use this variable separation, the Schrodinger equation gets simplified. You see the action of this Legendre operator on this wave function, which has r and y, is made, and when the lambda square acts on this y function, we get this second term in this potential energy. So, now we see that we have written down the Schrodinger equation, where this is the kinetic energy and this is effective potential energy. For the first term is the Coulombic interaction between the two, and the second term is the centrifugal force that arises when the electron goes around this nucleus in a fixed orbit. The orbital angular momentum of the electron generates the centrifugal force that keeps the electron from falling onto the nucleus. So, this effective Hamiltonian, this effective potential energy operator we discussed in our previous class. One other thing that you would notice here, that here we have this u of r, where we have defined our u of r, where in terms of the r, this is how we have defined. This is the r, capital R is the radial function. When I multiply this small r, the coordinate, with this r, we have defined this u function. Then what we have done is that we have introduced a dimensionless coordinate system rho, which is given as k r, where k is minus 2 mu e under square root h bar. And we have written down this differential equation of u of rho, where rho is the dimensionless coordinate. We needed to solve this differential equation. What we did afterwards is that instead of solving this differential equation directly, we looked at its asymptotic solution. One, when r, or the distance between the electron and the nucleus, is very high. The other is when the distance and the electron becomes very small. So, from these two asymptotic solution, if you remember, we obtain these two functions, e to the power minus rho and rho to the power L plus 1, and then we introduced, let the main body of the solution be given by this v of rho, another function. So, we have two asymptotic solution and the main body solution of the problem. What is in this function, these two quantities are known, but we still do not know this v of rho. So, therefore, we applied this u of rho in this differential equation and wrote down another differential equation, but this time the differential equation is written in terms of v and not in terms of u, where we have introduced the consequence of these two asymptotic part of the solutions into this equation. After that, so this is the differential equation we had in terms of v. Now, we have to define what is our v, and we defined our v as a power series expansion where Bj are the simply the coefficients of different orders of polynomials. So, here j goes from 0 to infinite, where the function is Bj rho to the power j. The advantage of expressing this function, the unknown function v rho, as a power series expansion is that we have the freedom to choose where to truncate this series. If our function is extremely complicated, we can define that function or describe this function by going higher and higher value of j, and if our function is extremely simple, then perhaps we will be able to explain it by truncating this series at some smaller value of j. This way of defining the wave function gives us the freedom to describe functions of different complexity. Once we have defined v of rho, then we have also defined the first derivative and the second derivative. You see, we obtained this because our differential equation has a second order term, a first order term, and v of rho. Now, we can use these terms over here in this equation. When we do this, the outcome of this exercise would be this, where we would be able to express B corresponding for j plus 1 in terms of B j. This relation is called recursion relation. The beauty of this relation is that from starting from B 0, for example, if you know B 0, you can use this coefficient over here and obtain B 1, and since you know B 1, you can use this coefficient to get B 2 and so on and so forth. Once you know the coefficients B 0, B 1, B 2, so therefore, you can express your V of rho, the function, and once you have expressed the V of rho, you have the final radial solution of this hydrogen atom problem. We will now continue our discussion from this point. This is the recursion relation that we had from the last slide. Now, you see, we have shown that this every time I have a B j using this relation, which is simply depends on j, which is the index of our expansion, L the orbital angular momentum, which goes from 0, 1, 2, so on and so forth. Rho 0 is a quantity that we had defined in our earlier class. So, if I know B j, I can always obtain B j plus 1. This would look like that this series that we have defined as V of rho as it would have infinite number of terms. But now, we would see whether we have any reason to see that this series should truncate somewhere or this series should stop somewhere. Suppose we consider a very large value of j, where j goes to infinite. In this case, we can write B j plus 1 is proportional to. So, I have, since j is very large, this term I can write as 2 j. Since j is very large than L and 1, so I am writing it as 2 j, and since j is very large, so I would expect that this would also be much greater than rho 0. So, I am writing only as j, and here I would write j plus 1 multiplied by j, where again j is very large compared to 12 and 2. This multiplied by B j. This, when you would look at, this would simply say you have 2 into j plus 1 B of j. In other words, I can write B j as, instead of writing 2 divided by j plus 1, I write 2 j minus 1. So, where j plus 1 is replaced by j and j is replaced by j minus 1. You see, B j is expressed in terms of B j minus 1, but I know I can express B j minus 1 in terms of B j minus 2. How would I do that? So, I have this term 2 over j, and then where I see these two terms is equivalent to B j minus 1. I am simply using this series. You would see now I can extend my discussion as to, I can simply go on adding more and more terms until I reach B 0, because you see my j minimum value is 0 and maximum value is not defined. So, I started with telling that let j be a very large quantity. In that case, I am obtaining this kind of expression. What I can simplify this further, as you see, I will have j number of terms here before B 0, and each term will have a 2. So, therefore, this term becomes 2 to the power j, and here j into j minus 1 into j minus 2 and so on. So, therefore, this becomes the j factorial multiplied by B 0. So, this is happening when B j is very large. So, therefore, you would see V of rho, if I apply this one over here, j goes from 0 to infinite. So, I have 2 to the power j factorial, and I am writing this rho to the power j here multiplied by this constant B 0. B 0 is the unknown coefficient in this power series expansion. So, this is a constant anyway, this is a coefficient. So, therefore, I am bringing it out and then I am simplifying this as when you look at this term, you would see from our we know that we can write e to the power x as x to the sum an infinite series of sum of x to the power n divided by n factorial, and when you look at this term, this would suggest that the second term is b 0 into e to the power 2 rho, because I have x here as 2. Now, this is happening when I am going for very large value of j. If you notice this function carefully, you would see that I have this function e to the power 2 rho as v. If you remember, we had defined u as having a term as rho to the power L plus 1 e to the power minus rho, and now we am seeing for very large value of j, v of rho becomes e to the power 2 rho. When I multiply these two terms, I get a term as e to the power rho, and I have a problem with this type of term, because if you remember when we were discussing the asymptotic solution of u of rho for large value of r, we saw that e to the power plus rho type of terms would diverge, and therefore, we cannot have this kind of functions in our this type of term in our wave function. So, we had discarded e to the power rho term, but now if we look at this power series expansion, we have got this problem. So, we are for very large value of j, our wave function would become e to the power rho kind of function, and this is unacceptable for large value of rho. So, we must do something for this. What can we do about it? We see that such a problem occurs only when j is very large or j goes to infinite. So, that means this series, this power series should not go to j equals infinite, rather it should truncate somewhere. It should have some value at which this series should, this power series should truncate, because I obtain this e to the power 2 rho term only when I define this summation where it goes from n equals 0 to infinite. If I had a finite term over here, I would not be able to express this term as an exponential function, and then in that case I would not have this trouble. So, therefore, to avoid this trouble, I say that this series must truncate somewhere. What do I mean by that? It simply means that there has to be some maximum value of j, let us call that as j max, for which, since this is the maximum value of j, for which b j max plus 1 should become 0. If b j max plus 1 becomes 0, that means this coefficient, which is the coefficient of rho j max plus rho to the power j max plus 1, when this coefficient becomes 0, that means that the power series would start truncating. Once I have j max plus 1 coefficient is 0, then j max plus 2, j max plus 3 and so on, all these coefficients will become 0. So, therefore, I have the power series will now be not an infinite series, rather a finite series. So, now what would we see? We require that what would be then this value of j max? What would be the maximum value of j where this power series should truncate? I have this expression for b j plus 1. Suppose let us say that I want to write this for j equals j max. When I write this, I would see that in the left hand side the b j max plus 1 will become 0, and that will happen when I look at the right hand side of this expression. This would be true only when I have plus when this condition is satisfied, then B of j max plus 1 will become 0 and my power series would start truncating, or I'll have only finite number of terms in my power series expansion. Now, let us look at this term carefully. J max is going to be an integer, because it goes for as j max is the maximum value of j, where j goes from 0, 1, 2 and so on and so forth. L is the orbital angular momentum of a particle moving around. So, its values are all integers. So, L goes, so here j max can have 0, 1, 2, so on and so forth. L again goes as 0, 1, 2, so on and so forth. So, this quantity in the left hand side is going to be an integer. So, j max is an integer, L is an integer, 1 is an integer. So, the sum of the 3 would be an integer, and let us call this as a new integer n, where n is defined as j max plus L plus 1. So, since you know that j max and L starts from 0, so therefore, n, the new integer, would start from 1, 2, 3 and so on and so forth. N equals 0 is not allowed, because this term has a plus 1 over here, and L and j max can mean their lowest possible value is 0. So, therefore, the lowest possible value of n is 1 and not 0. Now, we have this new condition is that the series will truncate when rho 0 is equal to 2n. Now, let us see what is our rho 0. We had defined this rho 0 as mu, which is the reduced mass of the system. In other words, which since it is reduced mass of electron and nucleus, so reduced mass of this two body system is going to be nearly equal to the mass of the electron. E, the charge of the electron, Z is the nuclear charge, 2 pi epsilon 0 comes from the permittivity, which is a term in the Coulombic interaction, and you have h bar square and k, which we defined as under square root of minus 2 mu e divided by h bar. I will rewrite this rho 0 in a slightly different way. Is all the terms over here. I simply took out Z, the nuclear charge, and k outside, and I kept the rest of the terms over here. You see, please notice here 2 pi epsilon 0 has become 4 pi epsilon 0, because I have it 2 multiplied over here. So, when you look at these terms, you see all these are constants. The mass of the electron, 4 pi epsilon 0, charge of electron, h bar square, all of them are constant. When you determine their value, you would actually find this one would turn out to be, we will give a small name to this one, which is 1 over A, where A's value is 0.529 angstrom, and this also has a popular name. This is known as the Bohr's radius. So, our rho 0 is expressed as 1 over A 2z by k. But now we say that rho 0 should be equal to 2n. So, we would now use both the information to see that 2z by A 1 over k is 2n. So, therefore, k is 2 cancel out, z divided by a n, and what is k? K is minus 2 mu e under square root divided by h bar equals z by a n, and then I take square of both sides. Then I have E equals minus h bar square divided by 2 mu a square z square divided by n square. Now, I see that I have this energy or E, which is given as minus h bar square divided by 2 mu a square, and which is again a constant. If you see the A, the Bohr's radius is a constant. H bar square by 2 mu is also another constant. So, therefore, let us give another name. E0 to this new constant multiplied by z square by n square, where E0, the value of E0 is 13.6 electron volt. Now, what I see is that I have these energy values of the hydrogen atom, which is equal to minus of E0, which is a constant here, multiplied by z square. Z is the nuclear charge. In case of hydrogen atom, it is 1, and divided by n square. What is this n now? We defined n because we had to truncate this series somewhere, and we have defined n as j max plus L plus 1, and whose values can be 1, 2, 3, so on and so forth. So, now we see that this energy E actually for a particular system where the nuclear charge is defined, this energy E is simply so this is my energy value. Now, for hydrogen atom where Z is equal to 1, if you put Z equals 1, then you would see the lowest value. So, here the energies are for n equals 1, 2, 3 and so on and so forth. For hydrogen atom when Z equals 1, so I have got only this term minus 13.6 electron volt. Lowest energy is obtained when n is equal to 1, and that value is simply minus 13.6 electron volt. That is the lowest energy of hydrogen atom. What is the next energy level? Next energy level I will get when I will apply n equals 2. When n equals 2, then you will see this is minus 13.6 divided by 4, and by using higher and higher values of n, I can determine the higher energy levels of hydrogen atom. So, in today's lecture, we had a review of the steps that we took to solve the quantum mechanical problem of hydrogen atom, and then we have now come to a position where we have written down the eigenvalues of the hydrogen atom problem, and by that we have now an idea about how the energy of these hydrogen atoms looks like, and we would continue our discussion from here in the next class. Thank you for your attention.